Hello to all. First of all, I wanted to thank the organizer for giving me the opportunity to present this result. This work is done at CEA Saclay in the SPEC laboratory and consists on the development of a local magnetic microscopy which combines magnetoresistive sensor and a scanning probe microscope. I will start by introducing you to the technique, what is a GMR and how the MRSPM works. Then we will look at the measurement made with it. So we don't want, yes. The principle is to incorporate a GMR sensor at the apex of the flexible cantilever. In this way, the deflection of the cantilever during the scanning of the tip in contact mode allows to measure the topography, while the GMR measures the stray field emitted by the sample. In this way, the topography measurement is decorrelated from the stray field measurement. Okay, for comparison, two typical imaging techniques in magnetic scanning probe microscopy exist, the NV center and the magnetic force microscopy. NV center can make quantitative measurement, but require optical detection and laser, while it is complicated to make a quantitative measurement with MFM. The use of a GMR allows detectivity of the order of nanotesla of roots per square hertz for a lateral magnetic resolution targeted of the order of micrometer. Okay, now let's look at how the magnetization measurement work with GMR. The GMR effect is due to spin effect, electronic effect. A GMR sensor is composed basically by two ferromagnetic layers separated by a non-magnetic and metallic spacer. The resistance of the structure depends on the relative orientation of the magnetic layer. To illustrate this phenomenon, here is a resistance versus field curve of a GMR tip. A high resistance is measured in the anti-parallel configuration and a low resistance in the parallel state. To have a magnetic sensor, one of the ferromagnetic layers needs to have a fixed magnetization, while the magnetization of the free layer is following the field emitted by the sample. And if the structure is well designed, then a linear variation of the resistance is measured around zero field. The sensitivity is given by the slope at zero. Thus, indeed, the stray field varies the orientation of the free layer of the GMR, which causes a variation of the resistance. Thus, when we observe a variation in the resistance of the GMR, we also observe the variation in the stray field emitted by the sample. Two other important things to note. The first is that the development of the GMR stack is more complicated than two layers, as shown in this diagram of the GMR use. And the second is that the sensitivity is important because it allows to go from the resistance measurement made by the GMR to the stray field value. So here is a diagram of the measurement made by MRSPM. The measurement of the topography is done with the apex of the cantilever. We don't have a tip under the cantilever. And in red, the position of the GMR on the cantilever, which shows the shift between the topography and the magnetic mapping. This shift depends on the angle of the cantilever with the surface, basically around 20 degrees, and the distance between the end of the cantilever and the position of the GMR, classically around 9 micrometers. The sensitivity of the GMR is along the axis of the cantilever. So the GMR is sensitive to the stray field emitting in the plane, mainly along the y-axis, but because of the angle of the cantilever, also on the z-axis, as you can see on this table. Tips are manufactured in the laboratory by standard lithography, sputtering, and etching process in a clean room. We manufacture a tip to be easily implemented on any commercial AFM. To realize this measurement, the probe has to be connected on a PCB support. Once the probes are fabricated, they are characterized to know their capacity to image a surface. We use a calibration sample with a nickel iron rod of 4 micrometer width and 40 nanometer thickness. The image has a topography measured with the GMR probe in a large scale and in a zoom. The resolution obtained is around of 10 nanometer in lateral direction and in the nanometer range in the Z scale. The nickel iron rod, 40 micrometer width, has a magnetization aligned with the long part of the rod. It created stray fields which are measured by the GMR. In the center, the topographic image measured with the MRSPM, and on the right, the resistance image measured by the GMR. By knowing all the electronic factors, gain, Wheatstone bridge correction, and the voltage applied to the GMR, and especially knowing the sensitivity of the tip that we have determined above with the slope of the resistance versus field curve, it is easy to obtain the stray field emitted by the sample. In this case, we estimate a stray field of 250 microtesla. So to check this measure, we realize a macrospin simulation with the following parameter corresponding exactly to the studied nickel iron rod. As I explained before, the tilting angle of the tip on the surface makes that the field perceived by the GMR is composed of the field emitted in the plane, on the y-axis mainly, on the z-axis. Here, I present the result of the simulation on the y and z-axis. For an easier comparison with the measurement made with the MRSPM, I extract a profile of these two images. And after, I add them up to their participation in the signal to get the theoretical signal by the GMR here in red. We can say that the field emitted by the nickel iron rod and the simulation are close and have the same shape. The results are in good agreement, but need to be improved with the imprecision due to the angle. We switch to another calibration sample to be able to compare it to a classical magnetic force microscopy measurement, a square of 50 micrometer side. As you can see on the MFM image made on this square, we get a result comparable to the bibliography. Here we have the measurement made with the MRSPM of the same square. The response is different from the MFM because this one measures the domain wall, this domain wall, while we measure the stray field emitted in the plane and out of the plane, which explains that the image is more complex. To understand this measurement, we have simulated the square with the vortex magnetization, and we perform a MUMAX micromagnetic simulation to obtain the magnetic configuration of the square. And taking into account all the elements, it is possible to estimate the stray field. We can see some similar form and intensity of field, even if the measured stray field are more complex than the simulation and need to be understood. To get an idea of the magnetic lateral resolution obtained with the MRSPM, we made a sample with a square whose distance decreased. As you can see on this image, with two squares spaced of 6 micrometers, we still have a dissociation of the signal emitted by the square. So we have a magnetic lateral resolution of about 5 micrometers. So to conclude, we were able to show the feasibility of this technique. We obtained topographic measurement with a relatively good precision and realized quantitative field measurement in pretty agreement with simulation. The next step is to study more complex material like magnetic petal, on which we have started to work. I want to thank all my coworkers. I want to thank again the organizer, and I thank you for your kind attention.